Now, later, when you keep on solving or writing shear moment equations, you don't need to draw the left portion of section AA. Instead, you just cover with the load diagram to the right of section AA. So as you cover with your paper to the right of section AA, if you have your papers, you cover the right portion of the section, then that will be the left portion of section AA. This one. You can see this left portion when you cover this right portion. And our segment AB, by the way, um, in segment AB, our X ranges from 0 to 5 meters. So this is now the shear equation for segment AB. You sum up forces vertical considering the left portion of the section. So to the left of section AA, there are two forces. One force acting upward. The other force is the resultant of that uniformly distributed loading. So that line of action passes through the center, and that distance is 1/2 of x. So the magnitude of the resultant for this loading is equal to the area of the load. So it is equal to the base times the height. The height here is the intensity of the load, which is 20 kilonewtons per meter. So there are two forces to the left of section AA. When you consider the left portion, upward force is positive, downward force is negative. So that's why we have this one. Now, for the moment equation, you sum up moments about this axis here, centroidal axis perpendicular to your monitor through that exploratory section there, no? Perpendicular to your monitor, and consider upward force causes positive moment and downward force causes negative moment. So the moment equation for segment AB is equal to summation of moments considering the left portion of the section. So we first consider the moment of this force. Since this is acting upward, we have positive moment, 63 times x. So we have here 63 times x. And then next is the moment of that downward force. So it causes negative moment. So minus 20x times x over 2. So that's why you have here x over 2. And simplifying, we have now this. It's 3x minus 10x squared kn meters. Okay, so that is to recall. And for the next segment, we do the same procedure. You pass an imaginary cutting plane passing anywhere between B and C. And you consider the left portion of section BB, and you apply the shear moment equations. And also here, for segment CD, you you pass an imaginary cutting plane CC anywhere between C and D, and consider the left portion of the section. Okay, so we will just uh, consider this left portion, no? So that others can understand clearly. I will just explain to you again how to write the shear moment equations for segment BC. So again, if you have a paper with you, then you cover the right portion of section BB and consider only the left portion. So when you cover the right portion of section BB, you can see this, okay? And for segment BC, the circulation for segment BC is equal to summation forces vertical, considering the left portion of the section. To the left portion of this section, we have two forces that are acting. This upward force, okay, positive 63, and then minus 100 gives you negative 37 kilonewtons. Okay, please do not hesitate, or please do not, yes, do not hesitate to ask questions, or you can interrupt me anytime you want. For the moment equation for segment BC, to sum up moments about the centroidal axis across that exploratory section. So that centroidal axis is perpendicular to your monitor. And we start with a moment of 63. So you have 63 times x. You have that first term there in the right side of the equation. Then the other force acting downward, minus 100 times x minus 2.5. Okay, that is x. And that distance there is 2.5. So the moment arm is x minus 2.5. That's the moment arm for that 100 kilonewtons. So we have now this one. Okay. And for um, the last segment CD, you can consider the same procedure. No, we do the same procedure. We pass imaginary cutting plane CC anywhere between C and D. So that imaginary cutting plane is located any horizontal distance x from the left end. So you cover the right portion of section CC, and or if you want, you draw the left portion, but it takes time. So to save time, you just cover the right portion of section CC. So when you cover the right portion of section CC, it looks like this one. Okay, so to the right, you have already your paper that is covering the right portion of section CC. And we start writing the shear and moment equations. So the shear equation for CD is equal to summation forces vertical considering the left portion of that section. To the left portion of that section, there are three forces. That force acting upward, so that's positive 63, then minus 100, then plus 67 gives us positive 30 kilonewtons. And then the moment equation for segment CD, we moment equation for segment CD, okay. I'm going to print screen this and paste it here. In our whiteboard. So the moment equation for segment CD is equal to summation of moments, considering the left portion of the section. So you sum up moments about that axis there, perpendicular to the screen, and we consider upward force again, positive moment. So we have 63 times x. Okay, 63 times x, then minus that moment of that force, 100 kN about that axis there. So minus 100 times x minus 2.5, then plus 67 times x minus 10, right? So the moment arm of this 67 kilonewton force about this point is x minus 10. So that gives us this. So we have now this one. And simplifying, we will arrive in here. Okay, 30x minus 420. And we enclose that with a parenthesis with a grouping symbol, and we write here the unit, kilonewton meters. Now, this is another way of writing the moment equation, the shear moment equations for segment CD. You see that to the right portion of section CC, we have only one force. Okay, so we will try, considering the right portion of section CC, we covered the left portion. We are considering here the right portion of section CC. And when writing the shear equation, we have here the shear equation for segment CD equals summation forces vertical. Consider summation forces vertical to the right portion, okay, to the right. That subscript capital letter R represents the right portion of that imaginary cutting plane of that section CC. So always remember that if you are considering the right portion of the section, an upward force is negative, while a downward force is positive. Okay? Okay, to the right portion of the section, I repeat, to write the shear equation, the force that is acting downward is positive, the force that is acting upward is negative. So we have only one force acting to the right. That force there, 30, and that is downward, so positive. So we have here positive 30. So if you compare that in here, we have also positive 30 when we consider the left portion of the section. Okay, so here there are how many terms to the right side? We have 1, 2, 3. Since there are three forces acting to the left, while in here, we have only one force acting to the right. So you can right away uh, write that shear equation. Okay, so we have positive 30 kN. And also the moment equation for segment CD, you sum up moments about the synchroidal axis there, perpendicular to your monitor. And regardless of the portion you consider, either to the left or to the right, always remember an upward force will cause positive movement, downward force will cause negative movement. Okay? An upward force will cause the beam to concave upward. So that is a positive sign convention for positive bending moment. A downward force will cause the beam to concave downward. So to concave downward, that is the sign convention for negative bending moment. Okay, so we have here downward force. That's why this is negative. So 30 times that moment arm is 14 minus x. And simplifying, we arrive in this moment equation. 30x minus 420, which is the same as this one here, 30x minus 420. Okay, this is formulated when we consider the left portion of the section. Okay, so I hope that is clear to you. Are there any questions? Questions? How many of you right now? There are 54. So, any questions? Questions? Silence means you fully understand or you do not understand. Are there any questions? Yes or no?
No, sir.
No,
Right,
sir.
good. Thank you. So now we proceed to sketching the Sharp moment diagrams. Going to make this bigger. Going to print screen. And again, I'm going to paste this on whiteboard. And we have here um, square equation for segment AB and moment equation for segment AB. Okay. So going back to this, we have this moment equation for segment BC, moment equation, square equation for BC, and moment equation for BC. This one here. Share equation and moment equation for segment CD. We have this going to print screen that one. Okay, so now the shear at A, when you use for the shear at A, no, we use the shear equation for segment AB because A is within segment AB. So we have here the shear equation for segment AB, 63 minus 20x. Now the value of x is 0 at A because our x distance is measured from the left end. So at the left end, x is 0. So the shear at A therefore is 0, 63. Okay, that second term there is 0. We have 63 kN. So that's why you have 63 here. And then the shear at B. Okay, so what is the shear at B? B is the boundary between AB and BC. So in this case, you can use either the shear equation for segment AB and the shear equation for segment BC. So either of those two equations in those two segments, AB and BC. We will just use the shear equation for segment AB. So at section B, the value of X is 5 meters. Okay, at that section, the value of X is 5. We have it here. Substitute that to this equation. Then that second term becomes negative 100. So 63 minus 100 gives us negative 37. So you have now here negative 37. So that point there is negative 37. And for the section where you can see a force, you should compute the shear considering an infinitesimal distance to the left of C. So when we say infinitesimal distance, that is a very short distance to the left of C. So that section is within BC. Okay, so the shear considering an infinitesimal distance to the left of C, that is within segment BC. So we use the shear equation for segment BC. Where's here? This is the shear equation for segment BC. So the shear at section C, therefore, considering an infinitesimal distance to the left, is negative 37. So we have here negative 37. You know, 50. And we determine the shear considering an infinitesimal distance to the right of C. Okay. So to the right of C, that is in segment CD already. So we use the shear equation for segment CD. So where is that shear equation for segment CD? For segment CD, we have this shear equation, 30. Okay? So that is why we have 30 here. Okay. And then there is no load. So this will be a horizontal line. And then we have there a load that is acting downward. So 30 minus 30 gives us 0. So this point here is 30. And to the right of D, to the right of that section D is 0. Okay? So this is now the shear. These are now the plotted points, and we connect the points for a uniformly distributed loading. It follows an inclined line. Okay, so we have here the connecting line, and then we connect the 2 points here with that line. Also, we connect the 2 points here with that line. I will tell you later why this is not curved. Why is it that this is a straight line? Okay, so that is when we proceed to the relation between the load, the shear, and moment. So for now, this is about determining the values of the shear and moment at the sections where we have the change of loading condition. Okay, so we proceed to the moment diagram. Okay, going back to this, I'm going to print screen this figure and paste it here. Okay, so we paste it here. Now, the moment at A, it's better to show all, no? Uh, the load diagram, shear diagram, and the moment diagram. Um, yeah. Okay, so I'm going to show this all. I'm going to print screen this and paste it on the whiteboard. Okay, so I hope you can still read these numbers. In my case, I can read this, and I'm sure that you can also read. So, so what is the moment at A? Now, the moment at A, um, we use the moment equation for segment AB because A is in segment AB. So where is that moment equation? We have going to paste it here for this one. So this one. Okay. Okay. So here, the moment at A. By the way, when before we drew the shear moment diagrams, we drew vertical lines right under the sections where we have the chains of loading condition. So these are the sections where we have the chains of loading condition. We draw vertical line right below. Okay, so we draw vertical lines, and then we draw a horizontal line representing the zero magnitude of shear. So we write here shear diagram, and then we write here V for shear, and enclose in parentheses the unit, kilonewtons. So we don't need to write the units after these values. After these values. Okay, so also for the moment diagram, we draw a horizontal line representing the zero magnitude of moment. So we write here moment M, enclosed in parentheses the unit. So the moment at A is equal to, we use the moment equation for segment AB because A is in segment AB. So at A, the value of X is zero. So here, the first term is zero minus zero. Moment equation for segment AB therefore is, or the moment at A therefore is zero. The moment at section A is zero. So that's why you have here zero. Or if you are going to apply the moment equation, the moment at A is equal to summation of moments considering the left portion of section A. There we have nothing to the left of section A. That is why the moment at A is zero. Okay, now in the shear diagram, at this point here, this is zero shear. Now, at zero shear, maximum moment occurs. So, from that zero shear, we project vertically upward and label that section where we have zero shear as section E. Okay, so we solve for the moment at section E. Now, before solving for the moment at section E, we need to know where is the location of E. Now, to find for the location of E, what we do here is we consider these similar triangles. That triangle is similar to that triangle. So, if that is X, then that distance will be 5 minus X. And since we have similar triangles, so we use ratio and proportion. 63 over X is equal to 37 over 5 minus X. Okay, so we can solve for X. X therefore is 3.15. Okay, or another way is we use the shear equation. Okay. The shear at E is equal to 0. Okay. So at that section E, the shear is 0. So this is equal to summation of forces vertical, considering the left portion of the section. So the left side of the equation is 0, and summing of forces vertical to the left of this section, we have that force acting upward, so positive, minus, consider that portion there. Now that has an area of x times 20. Okay, that is the resultant of that portion of the uniformly distributed loading. Okay, so you cover the right portion of this section, and the resultant is 20x downward. So that will be minus, so 20x. So you can solve for x here, which is also equal to 3.15. The same as when we use the ratio and the proportion, which is 63 over x is equal to 37 over 5 minus x. We can get value of x, which is also 3.15. So that is another way of determining the location of zero shear. So we label that section E. Now, why are we interested with the section that has zero shear? Because usually at the section with zero shear, maximum moment of course. And we are interested with that value because that is the designing value. We use that in the design. Also, the value for maximum shear, we use that in the design. So in this case, we know the value of x at section E, so we can solve for the moment at section E. So the moment at section E, that is, E is within segment AB, so we use the moment equation for segment AB. So the moment at E, therefore, the moment at E, therefore, is equal to 63 times 3.15 minus 10 times the square of 3.15. Okay? And it gives us this value, 99.23. Okay. So please check using your calculator. So now we proceed with the moment at B. If there are no questions. Okay, the moment at B is equal to, we use the moment equation for segment AB, or you can use the moment equation for segment BC if you want, because B is the boundary between those two segments. Now, in my case, we'll just use the moment equation for segment AB to determine the moment at B. So now the moment at B is equal to 63 times the value of x. At section B, the value of x is 5 meters. Okay, you see that it's 5 meters. Are there any questions? You can interrupt me anytime you want. Okay, so at B, I repeat, the value of x is 5. So you substitute it here. And also here, you will get now the moment at B equals 65. So that is now the magnitude of the moment at B. And then the moment at C. Okay, the moment at C, this time we use the moment equation for uh, segment BC, because C is it's a boundary between the segments BC and CD. So you can use either of the moment equations in those two segments. So the moment at C, we'll just use the moment equation for segment BC. Okay, so at C, the value of x equals 10, di ba? That's 5, that's 5. So C is located 10 meters from the left end. So we substitute that value of x in here, in here. So the moment at C is equal to 63 times 10. Uh, moment at C is equal to negative 37 times 10 plus 250. That gives us negative 120 here. Okay, that one there. And then the moment at D. Now to determine the moment at D, we use the moment equation for segment CD. So where's the moment equation for segment CD? This one. This is the moment equation for segment CD. At D, the value of x is equal to 14. Okay, this one. The value of x is 14 at section D. So substitute it here. We can solve now for the moment at D. The moment at D is equal to 0. Also, if you are going to use the moment equation, the moment at D is equal to summation of moments considering the right portion of the section. Now, we have nothing to the right of that section D. So therefore, the moment of D is equal to 0. And now we have already these points. We connect the points with this line. I will tell you later why we have a chord line and why we have this connecting line which is straight, and also why this is straight line. Now you see that at this point, this is the point with zero moment. That is the point with zero moment. And the point with zero moment is what we call that point with zero moment. That is what we call the point of inflection. The point of inflection. Okay, inflection. This is the point where there is a change of the curvature of the beam. You see that from that point to that point there, the the area here is positive area. So that means that this is positive moment. Okay, so that is from this point to this point. We project this point here with zero moment, vertically upward, and we label that section as section F. Now, here we have reaction. So there is a support here. And At C, we have also reaction, so there is another support. So if we are going to draw the deflection of the beam, it will deflect like this. It will deflect like this one. Okay, that one. So you see that here, this is zero moment. That is the point of inflection. That means that there is, at that point, we have the change of the curvature of the beam. In positive moment, from that left end, from that point to that point, we have positive moment. That means that the beam is concave upward. So that is the sign convention for positive bending moment. So that is why you have here concave upward. And then from this point to that point, we have negative moment. So meaning that the portion of the beam from here, from the point of inflection to the right end, we have a curvature that is concave downward. Okay, because we have negative moment. So you see here from that point to that point there, that is concave downward. Okay, because we have negative moment. Okay, are there any questions? So this is what we call elastic curve. If you look at this figure here, you can see this. This is called as elastic curve. Right here at this point, since there is a support, so there is no deflection at point C. Okay, in here, no deflection. So at point F, at the point where we have the zero moment, that is a point of inflection. That is the point where we have the change of the curvature of the beam from upward, from concave upward to concave downward. Okay, we have positive moment, concave upward, and here we have negative moment that's concave downward. That is the elastic curve. This one here. Okay. Any questions before we proceed? Questions? How many of you right now? There are.
Not so far, sir.
What is that, Chubb?
Not so far, sir.
Okay, good. Thank you. So we proceed with this one. Um, this one. Okay. Will you please read the problem? Can I hear somebody to, or can I hear somebody to read the problem? Any volunteer?
Hold on, sir.
Okay, thank you.
Write the shear and moment equations for the cantilever beam carrying the uniformly varying load and concentrated load shown in the figure.
Hmm.
Also, sketch the shear and moment diagrams.
Okay, thank you. So here we have what type of beam is this? What type of beam is this? Anybody? What type of beam?
Cantilever, sir.
Cantilever. Thank you. Cantilever beam. The left end here is free end. Okay, from point A all the way up to this point, it's a to the left of D, it's a free end, and right at that section, it's a support, and this is a fixed support. In a fixed support, there are three unknowns. No, we have a force that is acting upward, a force that is acting horizontal, a force that is acting horizontally, and a moment, a resisting moment. Now, since the loads here are purely vertical, the horizontal force is zero. So that's why you have only this upward force. And we call this V, shear. And the resisting moment is M, moment. You see that these loads will create a moment that is acting or that is rotating in that direction, counterclockwise. Okay, these loads, it will create that moment in that direction, counterclockwise. So to balance that, the resisting moment is clockwise rotation. Okay, okay. So we since we begin writing shear and moment equations from left to right, and since there is no support at the left, then we do not start solving for the reaction. Okay, so you consider the horizontal axis as our x, consider horizontal axis as x, and vertical axis as our y. Okay. So this point of intersection of x and y is zero. That's our point of origin. Now, we level the sections where we have the change of loading condition. Okay, we have these sections here where we have the change of loading condition, or those are the change of load points at A, at B, at C, and at D. Okay, so we start writing the shear and moment equations. No? So we start with segment AB. Start with segment AB. So for segment AB, or segment AB, uh, we uh, we pass imaginary cutting plane anywhere between A and B. Call this AA. So that AA is located any horizontal distance from the left end, any uh, horizontal X distance from the left end. So our X varies from 0 to 6 feet. So in mathematical form, we have 0 is less than or equal to X is less than or equal to 6 feet. Okay, so the shear equation for segment AB. The shear equation for segment AB, you cover the left portion, you cover the right portion of section AA. Cover the right portion of section AA. So when you cover the right portion of section AA, if you have your paper with you, you cover the right portion of section AA. Okay? And then you you use now the shear equation. The shear is equal to summation forces vertical considering the left portion of the section. So again, when you consider the left portion of the section, an upward force is positive while a downward force is negative. Okay, so if I were you, you get a paper and then you cover the right portion of section AA. Do you have your paper now? Yes or no? Do you have your paper? You cover the right portion of section AA. So now, what is um, so that you will understand? Okay, so when we cover the right portion of section AA, we have only this. We have only that part there, right? And this distance is x. Okay, now this part here, this one here, we do not know the intensity of the load right at that location. So we denoted by y. Okay, so this will be y. Now the resultant force is this force that is acting at the center, and that distance there is 1/3 of x, right? 1/3 of x. So our summing up force is vertical concerning the left. We have only one force, this force, and the magnitude of that force is equal to the area of that. So that magnitude is 1/2 times x times y. Okay. So we need to express y in terms of x. So how do you express y in terms of x? To express y in terms of x, we use this triangle. So this triangle here, small triangle, and that big triangle. So by ratio and proportion, we have y over x. Okay, that distance is x. So y over x is equal to 60 over 6. Right? So it's equal to, it's equal to 60. It's equal to 60. 60. It's equal to 60 over 6. So y therefore equals 10x. So to the left portion of this section, we have negative because it is acting downward. Minus 1/2 times x, y. This is negative 1 half times x times 10x. So this gives us negative 5x squared. That is the shear equation for segment AB. Okay. Now, what is the unit of this? Is it in newtons? That is in pounds, right? Okay. Now, what is the moment equation for segment AB? The moment equation for segment AB is equal to summation of moments considering the left portion of the section. So here, we have only that force acting downward. So this will be minus 1 half times x, y times the moment arm, 1/3 of x. Okay, so I hope you are following. So this gives us the moment equation for segment AB is equal to negative uh, 1/6, negative 1/6 x squared times y. So this gives us by 2, 3 by 2 is 5. Will be minus 5 x cubed, right? Divided by 3. Am I right? Ten x. 6 divided by 2 is 3. 10 divided by 2 is 5. So we have negative 5 x cubed over 3. Okay? The unit is in foot pounds. Okay. So, next is we um, we write the shear moment equations for BC. Okay, so we pass that imaginary cutting plane, call it BB, that is located in a horizontal distance x from the left end. So our segment BC will be going to move this now. So the shear equation, or by the way, for segment BC, our x bar is from 6 to 8 feet. Okay, for segment BC, our x bar is from 6 feet to 8 feet. Okay, x bar is from 6 feet to 8 feet, or in mathematical form, 6 is less than or equal to x is less than or equal to 8 feet. Okay, so what is the shear equation for segment BC? Now, for segment BC, you cover the right portion of this section. No? Cover the right portion of this section, and to the left portion of section BB, we have only single force. We have only that resultant of that triangular loading. Okay. or we draw the that you will understand. We have this left portion, no, of the section. This is 60 pounds per foot, and we have this resultant force that is acting right here. This is the resultant acting at the center, and the resultant force is equal to the area of that triangular loading. So that is 6 feet. So we have 1/2 times 6 times 60. Or this gives us 180 pounds. Right? So to the left of that section, we have only that force acting. So we have only minus 180 pounds. So that is now the shear equation for segment BC. Now the moment equation for segment BC is equal to summing up moments. Oh, it's equal to yes, summing up moments to the left of section of this section here. Sum up moments about that axis. So we have minus because that is the force here is acting down. So minus 180 multiplied by what is the moment arm? Moment arm is this. And this distance here, that distance is 2/3 of 6, right? That is equal to 4. So therefore, this moment arm here is x minus 4. That distance is x minus 4. Okay? So this is now x minus 4. So this will give us negative 180x plus 720. The unit here is 4 pounds. Okay? This is now the moment equation for BC. So what is the moment equation for CD or the shear equation for CD? We do the same procedure. We pass imaginary cutting plane, passing anywhere between C and D. And that is located x distance from the left end. So you try to cover the right portion of this section, CC. Okay? And now, the shear equation for segment CD is summation forces vertical, considering the left portion of the section. Considering the left portion of that section, we have the force that is acting here. This is the resultant of the triangular loading. So that is equal to 1/2. 1/2 times the base, 6 times the height, 60. So that gives us 180, right? So this is 180 pounds. So to the left of this section, there are only two forces acting. That force, that resultant, and that force. So negative 180 minus 200. Negative 180 minus 200. So this gives us negative 380 foot-pounds. Now, what is the moment equation for CD? For summation of moments from straight to left. So you sum up moments about this axis here. You cover this right portion of section CC. Cover the right portion of section CC. So what is the moment of this force about this axis perpendicular to the monitor? It is negative because this is acting downward. So minus 180 multiplied by the moment arm. What is the moment arm? From that force to that section there. That is x minus the distance 4, right? X minus 4. Okay. And then moment of that force about that axis perpendicular to the to that to that exploratory section. We are considering the centroidal axis of that exploratory section. So the moment of this force about this axis is negative 200 minus 200 multiplied by the moment arm. Now, what is the moment arm of this about this axis? It will be x minus 8, right? So x minus 8, x minus 8. So this gives us negative 180x plus 720 minus 200x plus this check, 1600. Okay. So this gives us negative 380x plus how much this? 2, 3, 20. Is that correct? 0, 0, 0. That's 2. 6 plus 7, 3 plus 1, 2. Okay. So this is now the moment equation for segment CD. This is what pounds. Okay. Any questions? Now, what about if we consider the right portion of this section? If you consider the right portion of this section, you cover the left portion of this section. This V here can be determined by static equation. Our V is equal to the sum of those two forces. So that is 200 plus 180, that's 380, right? Pounds. And what is the magnitude of the moment? To solve for the magnitude of the moment, take moments about D equal to 0. Okay. So I just write it here. Summing up moments about D equal to 0. Or the moment at D is equal to the sum of the moments of these forces. So the moment at D or M is equal to 200 multiplied by 2 plus 180 multiplied by, this is 6 plus 4 is 10, 10 minus 4 is 6, right? So this gives us how much? It's 400. 400 plus calculator. How much that? Can you give me an answer?
1 for 18.
1 for
18.
80. Okay, thank you. 1 for 80. Foot pounds. Okay, so we try, no? We try. So this is to find for the moment at D by using static equation, and this is the shear when we sum up forces vertical equal to 0. Okay, so these are now the shear and moment equations, and then you do the same procedure. No, you solve for the shear at A, shear at B, and then in here, since there is a force, you should determine the shear considering an infinitesimal distance to the left of C. So meaning a very short distance to the left of C, and also the shear considering an infinitesimal distance to the right of C. Okay, you solve for those shear forces. Okay, so uh, the the okay, we'll just draw the shear moment diagrams. Okay. I'm going to um, we'll draw vertical lines right under the sections where we have the change of loading condition. We draw vertical lines right under the change of loading condition. So that horizontal line represents zero magnitude for shear. So you write here 0, and then you write here shear diagram, and then well, you have here the unit kilonewtons. Then this will be 0. Uh, so it's a moment diagram, and then this is pounds, and this is 4 pounds. Okay, so what is now the shear at A? What is now the shear at A? What is now the shear at A? the shear at A. No, at A, x is 0. So here, when you substitute 0 to x, this shear at A is 0. So we have 0. So you write here 0. Then what is the shear at B? The shear at B, B is within segment AB, so you can use this. And the value of x is 6 feet at section B. So this will be 6. So 36 times 5. How much is that? 36 times 5?
180, sir.
180. Thank you. So that is negative, no? So this will be minus 180. Negative 180. You don't need to write the unit because we write already here the unit inclusive parentheses. And then what is the shear right at an infinitesimal distance to the left of C? To the left of C, that section, a very short distance to the left of C is within BC. We use the shear equation for BC. We have here negative 180. So this will be minus 180 here. Negative 180. Now what about the shear to the right of section C? That is within segment CD. So to the right, you use this, negative 380. Oh, that should not be foot pounds, so that should be pounds only. Okay, so negative 380. Negative 380 is here. And then we have that force going up. Negative 380 going up. So you see that that is the same value as this. So now I'm going to connect the points. The points looks like the connecting line looks like this. Scored line and then a straight line. And then, by the way, we have here 200. Now to the right of C, we have negative 380. So we forgot to write this. This is negative 380. And then we connect. So this is now the shear equation. And then you draw vertical lines. These are the intensities of shear. Okay. Now, for the moment at A, what is the moment at A? Moment at A is this is the moment equation for segment AB, no? So at A, the value of x is 0. So therefore, moment at A is 0. So we have 0 here because x is 0. Now what about the moment at B? B is within segment AB. So you can use this. Or you can use the moment equation for segment BC. So what is the moment at B using this equation? The value of x is 6. How much is this? That's negative, no? How much that? Negative. X is 6. So 6 cubed times 5 over 3. How much is that? Calculator?
360, sir.
360. Thank you. 360. Okay. Now, what about the moment at this section at C? Now, if you can see a moment right here applied at C, you need to determine the moment at an infinitesimal distance to the left and to the right. Okay, if there is a moment. Now, since there is a moment here, you can directly solve for the moment at C. You don't need to solve for the moment to the left and to the right of C. So in this case, what is the moment at C? Using this equation, this one, the value of x at C is located 8 feet from the left end. So we substitute it here. How much is our moment at C? If this is 8. If this is 8 feet, how much is this? What is the value?
Negative 720, sir.
Okay, thank you. Negative 720. Okay, so it's more or less twice this, more or less twice this, no? Negative 720. So it will be somewhere here. And then what is the moment at D? What is the moment at D? D is located 10 feet from left end. So we use a moment equation for CD. This will be negative 3,800, right? Negative 3,800. How much is that? Plus 2,320. How much is that?
1480, sir.
1,480. Thank you. So this is negative 1,480. So if you are going to check it here, you see you have 1,480 pounds. That's correct. So to connect the points, we have now this. Okay. You see that this is a curved line. In the moment diagram, it will also be a curved line, but it will be a third degree curve. This is second degree curve. This is third degree curve. This one here. This is a third degree curve. Why third degree curve for this? Because if you see here, moment equation for segment AB, we have x to the x cube. So the exponent here is 3. So that's why this is third degree curve. So third degree curve. Now, in here, you look at the shear equation. We have here x squared. That's why this is second degree curve. This one here is second degree curve. And what about this one? This is first degree curve. Okay. So first degree, second degree, third degree. Now to connect this points here, this is horizontal, so that will be uh, in the moment diagram, it will be straight line. That is straight. And also here we have horizontal line. In the moment diagram, it will be also straight line. So this is down the intensity of the moments So this is now the moment diagram. Okay, now if there are no questions, I'm going to explain to you the relation between the load, the shear, and the moment. Now, knowing the relation between the load, the shear, and moment, we don't need to write the shear and moment equations. We can directly we can directly sketch the shear and moment diagrams without writing the shear and moment equations, if we know the relation between the load, the shear, and the moment. Okay? So, going back to this, I'm going to close this. We have now this one. So this is about the relations among load, shear, and moment. So this will provide a method of constructing shear and moment diagrams without writing the shear and moment equations. I repeat, this will provide a method of constructing shear and moment diagrams without without the shear and moment equations. Okay, so kanina siya moment diagrams, shear and moment diagrams. Okay, so let me see. 7 na lang. Okay, so this is to derive an equation that shows the relation between the load, the shear, and moment. We consider here a beam with supports at both ends. So that's why you can see reactions, R sub 1 and R sub 2. Now, this beam is loaded with any combination of loading. In this case, we have this kind of loading. We have that load. So this intensity of the load is a function of X. And we will now consider a very small element, a differential element whose length is dx. Whose length is dx. One. Now we enlarge this element and we draw it here. So this is now the enlarged view of this element. And at this section, at the left end of the element, we have here a shear that goes up in this case, and a moment. Okay. Now, at the other end, at the right end, there is that slight change of the magnitude of the shear and moment. So we have here V plus dV, since we are considering a differential element whose length is dx. And we have here moment, which is slightly bigger than the moment at the left end. Okay, so the magnitude here is m plus dm. Now this load is acting upward, so that and this dx is very small, so the area is shown to be rectangular because dx is very small, and the area is the base dx times the height, which is the intensity of this loading right at this section, which is W. So the intensity here is W times dx. That gives us the resultant going up. And the line of action of this force is located 1/2 of dx from either of the ends. Okay? In this case, we have this distance dx over 2. Okay, please interrupt me if you have questions. Huh? So here, because this is an equilibrium condition, we can somehow force this vertical equal to 0, v plus dx, v plus w dx minus downward force d plus dv is equal to 0, and v will cancel. Okay, if we are going to simplifying, we have this v minus v will cancel. So you will have now w dx minus dv is equal to 0. So dv therefore equals w dx. All this as equation 1. Now there's the other static equation is summing up moments about b equals 0. So we have m, consider clockwise positive, we have m, and then moment of this force about point B, which is also clockwise, so v dx, v times dx, we have this. And then also the moment of this force about this point, we have w dx times the moment arm dx over 2. So we have this one here. Then minus this moment m plus dm equal to 0. So simplifying, we will have now this one. This m plus b dx minus m minus dm. Now what happened to this term here? This term will cancel. Why? Because this is very negligible. You see that dx times dx, this is product of differentials. And this term is negligible compared to the other terms, since this is a product of differentials. So this is negligible, we can cancel this. So now we have dm equals b dx. Okay? So we call this equation 2. And then solving for b equals dm dx. Now, um, we can rearrange this in this manner, dm equals b dx, and integrating, we have okay, from this equation here, can you see? If we are going to integrate this, we have this one. Okay, from b sub 1 to b sub 2. This is 1 here represents section 1, and this 2 here represents section 2. So from the shear at section 1 to shear at section 2. And here we have these limits from x sub 1 to x sub 2. And because the intensity is constant, you place it outside the integral sign. Intensity of the load is constant, place it outside the integral sign. So now integral dv is b with the limits b1 to b2. This is called the w. Integral dx with limits from x sub 1 to x sub 2. So this, we substitute this v1, v2 here to the variable v. So we have now v sub 2 minus v sub 1 equals the change in shear between the sections 1 and 2. And this integral dx is the distance x sub 2 minus x sub 1, or that is distance x. And distance x times w, that gives us the area of the load. So now, if there are no questions, we proceed from this equation here. We integrate this from integral dm from m1 to m2 equals integral b dx from x sub 1 to x sub 2. So integral dm is m So we substitute those limits. So m sub 2 minus m sub 1. This m sub 2 minus m sub 1 is the change in moment. So so v times integral dx, that is the area of the shear. Okay, so we have now this one, area of the shear. Okay, are there any questions? These are now the equations that we are going to use. And here, this is another equation to remember. This means that the intensity of the shear is equal to the slope of moment diagram. dm dx is the slope of moment diagram. And this one here, we can have W equals dB dx. Okay, solving for W, it will be dB dx. That means that the intensity of the load is equal to the slope of the shear diagram. Okay, W equals dB dx. Okay, so we have now this one. W equals dB dx, which is the slope of shear diagram. And this is the intensity of the load is equal to the slope of shear diagram. This is the intensity of the shear is equal to the slope of moment diagram. And in our geometry, we know that a line that is directed upward to the right is positive slope. And a line that is directed downward to the right, it has that negative slope. Okay, so we now go to sample problems. If there are no questions. Do you have any questions? Questions?
No, sir.
Okay, good. What about the ladies? I want to hear from the ladies also. Any questions from the ladies?
No question, sir.
Good. Thank you.
All good, sir.
Okay, thank you. So, here, using the semi-graphical method, sketch your movement diagrams for the beam shown in the figure. So this one here is a beam, and you notice that the left end is free end. This is support, and you can see reaction. Here is another support. So this is a cantilever beam. Um, in this case, we have this loading, combination of rectangular loading and concentrated load. The intensity of this rectangular loading is 2 kilonewtons per meter. The intensity of this load is 8 kilonewtons. Okay, so we solve first for the reactions. Use the static equations, summing up moments about D equals 0. You can solve for this. And summing up forces vertical equals 0. You can solve for other reaction. And if you want to know, or if you want to verify the magnitude of this, you can sum up moments about B equal to 0. Okay. So after solving for the reactions, we draw vertical lines. We indicate the change of load points, the sections where we have the change of loading condition. So we have this section A, this section B, this section C, and that section D. And then we draw vertical lines right under those sections. So we have now these vertical lines. This one. Okay. Okay, so now the shear at A, the shear at A is 0, no? Why? Because when you use the shear equation, the shear at A is equal to summing up forces vertical to the left portion of section A. We have nothing to the left. That's why you have 0 here. Okay? So this is a horizontal line representing 0 magnitude of shear. So we write here shear diagram. Unit here enclosed in parentheses, kilonewtons. Now, since there is a force here, you need to solve for the shear considering the shear at infinitesimal distance to the left and infinitesimal distance to the right because of that force. If there is a moment right here, you need to solve for the moment at infinitesimal distance to the left and also at infinitesimal distance to the right. If there is a moment. Now, in this case, there is a force. So from I'm going to use this. So you have here the intensity of the shear to the left of V. Okay, you see, to the left of V, we have this part, and you have this force here. This one here. This is the resultant of this portion, and this force equals the area of this. That is 3 times 2. So that is 6. So 0 minus 6 gives us negative 6. And negative 6 plus 20 gives us positive 14. And then 14 minus this area, minus this area here, the resultant of this. This one. This force is equal to the area of this load, this portion of the load. So that is 9 times 2. So this is 18. So 14 minus 18 gives us negative 4. And negative 4, again, we have that force acting. So you need to determine the shear to the left and to the right. So we have negative 4 here, and then minus 8. Minus 8 is negative 12. So this is negative 12. This one here, negative 12. And negative 12, there's no load here, so this will continue to be negative 12. And then plus 12 gives us 0. The shear to the right of this, the shear at D is equal to, using the summing up forces vertical to the right. There's nothing to the right, so the shear here is 0. Okay. So now we will connect the points. Now to connect the points, we use the equation. The intensity of the load is equal to the slope of the shear diagram. Slope of shear diagram. So this is the relation between the load and the shear. Now you see here. Are you still listening? Yes or no?
Yes, sir. Yes, sir.
Yes, sir.
Okay, but what about reading? Are you still listening? Papa, so 5 minutes na lang. No? Okay, so from here to here, the intensity of the load is negative. Why negative? Because that's downward. And the intensity of the load here is constant. Okay. So it follows that we have here a negative, this is the intensity of the load, negative constant intensity of the load corresponds to slope of shear diagram. So for a negative constant slope, it will be that one. So this is negative slope. This is negative slope directed downward to the right and constant slope. It's a straight line. So that's why you have here this connecting line, a straight line. Okay. Then there is an abrupt rise of the shear because of that force. Then from that point to that point, from B to C, we have negative intensity of the load because that's downward and constant intensity of the load. So we have negative constant intensity of the load corresponds to a negative constant slope of shear diagram. So for a negative constant slope, it will be a line that is directed down to the right. Negative constant slope. That's why you have here that line. Negative directed downward to the right, negative slope, and constant slope. That is a that line has a constant slope. Okay. Now from C to D, the intensity of the load is zero. So it corresponds to zero slope of shear diagram. So that's why we have horizontal line. It has zero slope. Okay. So what about this one? The moment at A is equal to zero. When you use the moment equation, the moment at A is summation of moments to the left portion of section A. So to the left, we have nothing to the left. So the moment at A is zero. The moment at A is zero. Okay. I'm going to print screen that one. That I can write. Okay, so the moment at A, I repeat, is equal to, when you sum up moments considering the left portion, you have nothing to the left, that's zero. Now, what about the moment at B? The moment at B, in here, is equal to the moment at A plus the change of the moment. The change of the moment is, we have M sub 2 minus M sub 1. This is equal to the area of shear. Okay. The area of shear. That is from this equation here, you see from here, M sub 2 minus M sub 1 from this, when we integrate, M sub 2 minus M sub 1 equals the change in the moment, which is equal to the area of the shear. So the area of the shear from A to B is this area. It's a negative area. So this is equal to minus 1/2 times 3 times 6. This gives us negative 9, right? kN meters. So that's why you have here negative 9. This is negative 9. Okay. Now, what about the moment right here at zero shear? You need to solve for this distance, x. Okay. By ratio and proportion. So we can solve for x here. X7, 9 minus 2 is 9 minus 7 is 2. So this one here is 7, and this one here is 2. From this ratio and proportion. Time check is already 9:01. Um, I'm going to continue this on Tuesday next week, face to face. Okay? So I'm going to end now this and go back to this one here, stop presenting. Okay, so I'm going to show myself. I'm of you right now. There are 45. Okay. Okay, so I hope you learned.